Hello class, today we'll be going over section 9.2, testing the difference between two means using the t-test. So I'd like to jump right into it, but again, like you would in class, just go ahead and take some notes as we're going along so that you can kind of keep up with it a little bit better and make your homework go a little bit easier. So they start off with the formula for your t-test. So in any hypothesis test, there's a different test statistic formula. In this section, when you're testing between two means from samples, we're going to use that t-test, which is a pretty gnarly formula. It's x bar 1 minus x bar 2 minus mu 1 minus mu 2 over the square root of s1 squared over n1 plus s2 squared over n2. Where degrees of freedom is the smaller of n1 minus 1 or n2 minus 2, depending on the sample size of both of your samples. Now, some assumptions that are important before you even begin to use these procedures: both samples have to be from random samples. 2, the sample data are independent of one another, and the sample sizes are less than 30, or when the sample sizes are less than 30, the populations must be normally distributed or approximately normally distributed. So with this said, I'd like to jump into the example that we have here for the weights of children. I'm going to go ahead and read it, and we're going to get some follow the hypothesis testing, kind of the same format that we've been seeing in class. So a researcher wishes to see if the average weights of newborn male infants are different from the average weights of newborn female infants. She selects a random sample of 10 male infants and finds the mean weight is 7 pounds 11 ounces and the standard deviation is the sample is 8 ounces. She selects a random sample of 8 female infants and finds that the mean weight is 7 pounds 4 ounces and the standard deviation of the sample is 5 ounces. Can it be concluded at alpha equal to 0.05 that the mean weight of the males is different from the mean weight of the females, assume that the variables are normally distributed? So I like to start with the step 0 in the hypothesis testing. And my step 0 is, what do they give us in the problem? So as far as I can see, they give us a random sample of 10 male infants. I'm going to call that N1 is 10. They also give us a mean of 7 pounds 11 ounces. Okay, 7 pounds 11 ounces, which we probably want to convert to ounces. So we know that there's 16 ounces in a pound, so 7 pounds 11 ounces, 7 times 16 plus 11. I did a quick calculation, you get 123. So that's my x bar 1 from my first sample, 123 ounces, because I'm going to want everything in the same units. What else do they give us in the problem with the standard deviation of 8? So the sample standard deviation is 8. Now notice here we have S instead of the population standard deviation. So that's kind of what's going to distinguish this section from the previous section, that you have a sample from or a sample standard deviation rather than a population standard deviation. So they also give us for the second sample that there's 8 females. So we're going to do, and I might even want to label this one for male just for myself, and this is for female. So N2, there was 8. X bar 2 on the problem was 7 pounds 4 ounces. So 7 times 16 plus 4, that's 116. So x bar 2 is 116. And also a sample standard deviation of 5 ounces. Okay, so I have my step 0. I listed my statistics that I can get. Maybe also throw in there alpha is 0.05. So we'll go from there. Okay, so it says state the hypothesis and identify the claim. So I want to tell whether the population of males has a mean weight that is different from the population of males. How do I know? I want to tell if it's different. Well, it says can it be concluded at alpha equals 0.05 that the mean weight of males is different from the mean weight of females? So that's what's going to tell me. So I'm gonna write my step 1, which is my null hypothesis, and I'm going to say that the mean weight of 1 is the null is that they're not different, right? We speculate no difference. The alternative is where we're going to say, yeah, that they're different. Now, keep in mind this can be written in one of two ways. An alternate way to write this is if you subtract mu2 from both sides, what are you left with on the right side? 0. You could also say the same thing here. Subtract. In other words, this is saying that the mean of the differences between mu1 and mu2 is 0. Is equal to 0 is the null, and it's not the difference between the two is not equal to 0 is the alternative. Equivalent statements. Now you do want to say something about what these are, so you would say maybe where mu1 is the true mean weight of males or infant males or male infants, and mu2 is the mean weight of female infants. Okay, just kind of defining what mu1 and mu2 is there on step 1, and really we call this step 1. So step 2 in our process is find the critical value. So we use the critical value method at alpha equals to 0.05 at two-tailed test. Okay, so step 2, to find the critical values, like we said, we're going to go ahead, we know it's a two-tailed test, so alpha on both sides, I would need to do alpha over 2, which alpha over 2 is 0.025. Okay, so that means I need to take inverse norm 0.025 or look for the z-score at 0.025. You know that I prefer using a calculator for this, so I'm just going to use inverse, take that back, I'm sorry, inverse t, because we're talking about the t-test, because we have a sample, and with degrees of freedom being the smaller of the two, so the degrees of freedom here would actually be the smaller of the two minus 1, so it's going to be 4. Okay, because the smaller, take that back, not s, but your n's, so it's 7. Okay, so when you do this, you got to do inverse t of area 0.025 and degrees of freedom of the smaller of the two n's, which is 8 minus 1, 7. So that would be 7. Then you just push enter and you'll find your t critical, which I get to be negative 2.36. So t critical equals negative 2.36. Okay, and then by symmetry, the other one is positive, or positive t critical is 2.36. Okay, so that's how you find your t critical. So step 2 is done. Next, we find the test statistic. So let me take a second. I'm going to write the formula up. Okay, so I have the formula that's on your papers. Now, to find the t-test, nothing to it, just input the numbers into the formula. So let's go ahead and jump into that. So t-test, x bar 1 is 123, minus x bar 2 is 116. And here, based off our assumption, mu1 equals to mu2, therefore if you subtract them, they should be 0. So I really don't need that part of the formula in this case. So over the square root of s1 squared, which is 8 squared, over n1, which is 10, plus s2 squared, which is 5 squared, over n2, which is 8. Then you just input into the calculator and you'll find an answer. Okay, so after inputting, I get 2.27. So then we can make a decision. I'm going to kind of use my picture over here. So the T critical is 2.36, 2.27 will be slightly inside. So our T test will fall inside of that, meaning what is the decision? Do we reject or do we fail to reject the null hypothesis based off the critical value method? Well, the decision would be we're going to go ahead and fail to reject since it's inside, it's in the non-critical region. So step 4, make our decision on H naught. We fail to reject H naught that the mean birth weight of males is equal to the mean birth weight of females, or infant weight. So now we're going to make a statement about the alternative, or conclusion about the alternative. So here we're going to say there is no evidence to suggest H1 that the mean birth weight of males is different from the mean birth weight of females. And that concludes our hypothesis test for this question. Okay, so as a follow-up to the same question for the weights of newborn infants, we want to answer the question for a 95% confidence interval for the difference between the means of the males and the females infants. So using the same information, also using a 95% confidence interval, alpha would be 0.05, so alpha over 2 would be 0.025, so we'd still need to do inverse T of alpha, or area, equal to 0.025 with the same degrees of freedom, which is 7 from the smaller of the two, which we already did, although I erased it, but I have it here. It's negative 2.36. In other words, T alpha over 2 is positive 2.36 by symmetry, because we want the positive T alpha. So using that, we just go ahead and start plugging away. We have all our information, so we're going to do 123 minus 116 minus 2.36 divided by this, or multiplied by the square root of 8 squared over n1, which is 10, plus s2. Oh, I realize I put s1 here. So that should be s2. s2 is 5 squared over n2 is 8, less than mu1 minus mu2, less than the same thing, plus right here. Okay, and then it's just a matter of inputting it into your calculator. So after inputting this, I get negative 0.28. Less than the difference between the populations of boys and girls. And over here I get positive 14.28. Now let's think about this. So and interpret the results a little bit. So since this contains 0, that shows evidence that there is no difference between male infants and female infants. That's what the confidence interval suggests. Okay, so we can write something. So here's the confidence interval, and we can say something like, since the interval for the difference between males and females contains 0, this is evidence to suggest that mu1 equals to mu2. Okay? And so that's how you conduct the hypothesis test. And section 9.2 is done. But just some key things here that differ from 9.1 is that the fact that you had 2 samples that were independent of each other, and you had to use S. So with S, and from a sample, you're going to use T, whereas before you had the population standard deviation, so therefore you use Z critical versus T critical and the T test. So this is all about T test and T critical, versus the previous one was about Z test and Z critical.